Okay, welcome to Swell Academy. Today we're looking at finding a limit using trig identities. We'll mainly be using a double angle here. The first thing you want to consider in any of these is, are we able to do substitution? And what you see this problem presents to you is sine of theta at pi over 2 is equal to 1. So in our denominator, we would have ended up at 1 minus 1 or 0, therefore indeterminate. So our next step is actually, can we use trig identities? Can we factor? Can we eliminate? Can we plug some holes in order to hopefully get to a limit? So first thing I want to do is look at this top piece here, and you see the sine squared. It can be split into sine 2 theta, sine 2 theta. That is essentially what sine squared 2 theta is. And then underneath, when you have a sine, basically the first alarm or kind of thought that should pop in your head is, ooh, sine squared theta. That's my Pythagorean identity with trig. And what that identity is sine squared theta plus cosine squared theta is equal to 1. And if we subtract cosine squared theta from both sides, we actually end up with sine squared theta is equal to 1 minus cosine squared theta. So we could use this piece to replace our sine squared theta. So in rewriting it, we get 1 minus basically 1 minus cosine squared theta. So what we did was essentially took this piece here and then replaced it here. So you'll see a lot of substitution and replacement using trig identity. That's one piece. The other trig alert that should go off is this sine 2 theta, which is a double angle identity where sine 2 theta is equal to 2 sine theta. And you could make a sheet, or let's say a key sheet. I don't want to call it a cheat sheet, where you have these identities that you could use for replacement. And that's what we're going to do underneath here. We're going to say, okay, this becomes, this piece here is going to replace our sine 2 theta. So we're going to say no longer sine 2 theta, we're going to say 2 sine theta over, or I'm sorry, cosine theta sine 2 theta. And underneath, we end up with 1 minus 1 plus cosine squared theta. What I've done is I've distributed the negative sign to each. The ones cancel out, and you're just left with cosine squared theta on the bottom. And cosine squared theta can be written as cosine theta times cosine theta, because it is squared, so it is multiplying itself. So I can rewrite this as cosine theta cosine theta. Now in most, this should essentially fix all our problems. Let's say plug the hole. Well, eliminated that. Should plug our hole, but recognize that, let me just rewrite this and I'll illustrate something to you, that we are looking at, as x approaches pi over 2, and at pi over 2, cosine is equal to 0. So essentially although we're able to factor, it is again resulting in an indeterminate limit or a limit that does not exist. But let's not forget that, well, we have another trig alert here, right? And ooh, that's sine 2 theta. Well, I can again use my double angle, which we're using here, and again replace 2 sine theta, my sine 2 theta with 2 sine theta, cosine theta. And what that does, it actually allows me to again factor out a whole or piece. So basically it allows me to factor out a cosine squared theta. Now what I'm left with is, if I were to multiply these two together, I'm left with, let me switch the color up here, a limit of 4 sine squared theta. And at pi over 2, sine is equal to 1. So essentially what I'm saying is 4 times 1 times 1. If sine of pi over 2 is equal to 1, then I'm essentially replacing this sine over 2 sine squared theta with 1, and my limit actually ends up being 4. So my limit, I would rewrite this as a limit. Some put the 4 as a coefficient limit, but just for focusing on finding another limit purposes, we factor out this 2 sine theta becomes 4 sine theta squared, and as x approaches pi over 2, it results in a 4 sine squared theta, in which sine theta at pi over 2 is 1, and you end up again with that 1 over 1. Now, finding these values of, what is sine theta at pi over 2, you want to refer back to your unit circle, and pi over 2, or half a pi, would be over here, and you would see that value for sine is going to be 1 here. Approaches to solving your trig identity. So here I've kind of set up a separate approach, some of it being the same, where I replace the sine 2 theta with the 2 sine theta cosine theta. We did that in the previous problem. But what you see here is that I've actually turned 1 sine squared theta into a cosine squared theta. Now, how did I do that? Well, if I subtract sine theta squared theta from both sides, I end up with a cosine squared theta is equal to 1 sine squared theta. So, and in replacing that, I actually again get to that point where I have 2 cosine thetas underneath, and where I could cancel out, and we know, the rest is history from there. So this is just a quick little alternative approach here, just in case if you don't see to replace that sine squared theta with the 1 minus cosine squared theta, which we did. Instead, we're replacing the 1 sine theta or squared theta with, we're replacing it with cosine squared theta. That's the difference between the previous attempt and this attempt. Both result in the same answer of a limit of 4. And again, I think this is, and the last thing I want to point out on this slide here is, and why this is such a great problem, is that it's using a double angle identity. So that's good to experience, having our tool belt, and then it also brings us to a Pythag identity, which is good to use. But my favorite part about this problem is, usually when you factor out, or as AP Classroom talks about, plug the hole, we think we're okay, but then we look at cosine at pi over 2 as, because that's what it's approaching. We recognize that's a 0. So in this case, we again have this idea that, we have a limit that does not exist. And What this problem pushes us to do is actually go another layer, go another level, use our double angle, or DA, or double angle identity, once again to further factor out certain pieces and come up with our 4 sine squared theta. So another great question. Take some time, take some experimentation. Again, the more you fail, the more you succeed, and hard work is always a necessary ingredient.